This time we'll be talking about multitask, multi-domain, and multilingual learning. And these are all kind of closely linked together, very important, kind of building off the ideas from pre-training that we had last time. So I'm first going to try to give you kind of a general conceptual idea of some of the challenges and opportunities that we face in multi-domain or multitask or multilingual learning problems. And hopefully that will give you a framework to think about, like how difficult your problem is, what types of methods might be applicable to your problem. And then after that, I will go into some, specific methods that we use to solve these. Okay. So multitask learning, everybody heard about this last time. And basically the idea is that you want to train a model that is able to do well on multiple tasks at once. So you have this is an example, and you have your encoder, and then you have your language model and your tagging. This actually started to come out right near the end of the popularity of the first neural network boom. And so neural networks are a very good match with multitask learning because they learn internal representations and you can use them for multiple tasks at once. A piece of trivia, this Caruana 1997 paper is basically a CMU PhD thesis. So it was called, I think, multitask learning, literally. So if you're aiming to do a PhD, you can aim to do a PhD that's as impactful as that one. So. Okay. Applications of multitask learning. Basically, one of the main times when you want to do multitask learning is when one of your two tasks has fewer data than the other ones. So
we can't see the slides.
Oh, thank you. Thank you for telling me. You should be able to now.
Yes.
Okay, thank you. Sorry about that. Okay. Fortunately, they were all slides you saw yesterday, so we're starting the new ones now. So applications of multitask learning. So we want to perform multitasking when one of the two tasks has fewer data than the other one. Plain text to labeled text is the one that I mainly talked about last time, where we're doing pre-training of a language model and applying it to some sort of thing where we need hand-labeled data, so it's not very easy to get lots of data. Another very popular one, which we're going to talk about more this time, is a general domain to specific domains. So this could be for example, going from web text to medical text. This is very important because, if you are going to build practical systems, it's almost always the case that the domain is not going to be Wikipedia or not going to be just general web text. Another very important use case is high resource language to low resource language, or high resource language variety to low resource language variety. So this could be anywhere from doing something like wanting to train on English and then transfer to another language like Telugu, or it could just be wanting to train on English and transfer to English, but a different variety of English. So, you're training on Wikipedia, but then you want to be transferring to social media or something like that. So talking a little bit more about methodology. So I got a question on Zoom. Is it better to multitask learn or SSRL, where SSRL is probably self-supervised representation learning? So this is a good question. Self-supervised learning. We've talked about, I guess, unsupervised learning, maybe. Learning and supervised learning. And kind of in general, unsupervised learning often looks like this. It looks like, the language modeling problem where we have just inputs and we want to model them. Supervised learning looks like usually something like this, our discriminative text classification problem. Semi-supervised learning, how would people define semi-supervised learning? Any ideas? Yeah.
We are very few supervised labels at first, then predict pseudo labels and then use that.
You have very few supervised labels, and then you predict supervised labels, and then you iterate on that. Close. I would actually call that self-training. Specifically that, I would call that self-training. So that's another thing. Yeah. Oh, the labels are weak. That's a great point. That's actually often called weak supervision. And that's also another interesting learning paradigm, where like the labels might be something correlated with the true answer, but not actually the true answer. So one example of that would be if you extracted noisy data from Wikipedia for named entity recognition that wasn't right all of the time, but it was right some of the time, and use that to train a named entity recognition. Yeah. So take some support other than the actual data. Yes. Yeah, that's basically true. I got another answer on Zoom, which is maybe a good one, which is labels are only available for part of the data. Part of your data has the labels live that you could be using here, part of the data doesn't. And that's kind of the traditional definition, like you do unsupervised learning and supervised learning together. So actually pre-training and fine-tuning is a variety of semi-supervised learning. It's a specific variety, but yeah, yes.
So you have some label data and unlabeled data. You do this unsupervised clustering, and then based on the cluster form, you sort of self-label the clusters that are formed. So whatever unlabeled in the cluster that's labeled, if they have whatever is labeled in the cluster. Would that sort of fall into one of these 4, 5, or is that its own thing?
If I understand what you're talking about, it might be something like self-training, I guess, or weak supervision. Like yeah, maybe it'd be weak supervision because like the labels wouldn't be perfect, right? So yeah, so that's a good point. The people on Zoom asked me to repeat. It'd be like, what if you did some sort of unsupervised clustering and used the clusters to kind of indicate the labels? And I said that would be weak supervision because the clusters would be like pseudo labels, but they wouldn't be correct all the time. Okay, so I went through a bunch of terms here, and we have like semi-supervised, which usually takes from whole. So what is self-supervised learning? Yeah.
Mass language modeling.
So a mass language modeling is a type of self-supervised learning. Any ideas? You create the labels yourself. Yeah, you also create the labels yourself when you're doing self-training. Like a generator discriminator label paradigm. So again, I don't know if I'd call again self-supervised learning. I actually haven't thought about it carefully enough, but I think it's usually not put in that paradigm. So I got an answer on Zoom, which I do think is a good one. So basically it says, the input is used as labels for a task that helps learn representations. So basically, a way I've heard it described is it's self-supervised learning is a particular type of self-supervised learning is a particular type of unsupervised learning. It's particularly the type of unsupervised learning where you are solving a prediction problem that looks like a supervised prediction problem. So mass language modeling is a little bit like that, because basically you're doing some perturbation to the input, and then you're solving a classification problem over the words in the output. So that's considered a self-supervised learning problem. What would unsupervised learning that isn't classified as self-supervised learning be? Yeah. Reinforcement learning is usually actually a different, considered neither unsupervised or supervised. You could also consider it weakly supervised, because you're getting a reward that's not telling you all of the actions you need to be solving, but yeah. Yeah, K nearest neighbors, or like a nearest neighbors clustering algorithm. So a nearest neighbors clustering algorithm induces some sort of structure over the input, but you have no supervised training algorithm. It just has some sort of clustering criterion. So mass language modeling would be self-supervised learning. Mass language modeling and clustering would be unsupervised learning, but like mass language modeling would be self-supervised learning. Yeah, I saw a Gaussian mixture model would be another example of unsupervised learning, which is kind of like soft clustering. So anyway, this is an aside, but you hear these terms a lot, so it's usually a good idea to know what they mean. Going back to the original question, which was, is it better to multitask learn or do self-supervised representation learning? So I think self-supervised representation learning is basically a type of unsupervised learning that can be used within multitask learning. You have one self-supervised objective, you have one multitask objective, or you have one supervised objective, and you could use them together. So basically, self-supervised learning is usually used together with multitask learning. I had a question, can I give an example of semi-supervised learning? So one example of semi-supervised learning would be doing a mass language modeling objective to learn BERT, and then fine-tuning BERT on another like task or something. So that's semi-supervised, because when you train BERT, you're using unlabeled data, but when you fine-tune BERT, you're using labeled data. So yeah. Basically, your data is what drives what kind of method is does your data drive what kind of method you're using to solve the problem? Yeah, I'd say that's usually the case. Yeah. If you have like a multi-stage setup, but have labels only for the end stage, is it counted as weak supervision? For example, you have emotion detection and then you use it to say detect depression or something, and you have labels only for the depression detection or something. What was the you have something and then you use it to have like you perform emotion detection and then you use it to classify whether someone is depressed or not, and you have labels only for that task. Then is it weak supervision? Okay. Okay, so the question is, if you have like emotion detection and you get labels and then you use that to detect depression, how would you learn your emotion detector? Like after the emotion detection, you have a differentiable step, and that works through the entire. Yeah. So if you have a differentiable step and backprop into the emotion detector, I would say that is supervised learning of the depression detector and weakly supervised learning of the emotion detector. Yeah. I mean, for example, if you just build a multi-layer neural network together, or you can just say that at some point from there will essentially give you emotion representation. So this multi-stage is kind of be looked at. I mean, if there's a differential step between emotion representation and depression, it would just sort of become one full stage. Yeah, and so then wouldn't this become one full neural network? Yes, it could become one full neural network. I'm actually going to talk about this later in the slide. So yeah. let's- Actually, that's a really good point. So why is self-training a different concept than weak supervision? I would say self-training is maybe a variety of weak supervision. So it's like a subset. Yeah. So yeah, so basically self-supervised learning is a subset of unsupervised learning, and self-training is a subset of weak supervision. It'd be kind of nice to draw a like Venn diagram or something like that. We can let me take a picture and we can do that. Oops. Okay. Great. So that was a bit of an aside, but you hear these terms all the time, so I think it's a good idea to have some examples of them. So now I'd like to talk about a little bit more advanced multitasking methodology than we talked about in the previous time when we were just talking about pre-training and fine-tuning. So some of the things we're going to talk about today are what parameters do we update and how do we sample or weight our different tasks. But before I get into the multitasking methodology part, I want to kind of lay out some basic ideas and like distribution shift and other things that are necessary for understanding like why and how we do things. So the first thing I'd like to talk about is domain adaptation. And I talk about domain adaptation, and what do we mean by a domain in NLP? And basically what we mean is we have one task, but incoming data could be from different distributions. So for example, we could have news text, medical text, spoken language, and we want to do translation of all of these texts, and the input text is different. This is traditionally called domain adaptation only when we are doing the same task as opposed to multiple tasks, but you could kind of view it as a variety of multitask learning if we say news translation and medical translation are different tasks. Sometimes the domains are labeled, sometimes they are not. So in the better case, you have domain labels. In the worst case, you don't. So what's in a domain? And I'd suggest taking a look at this paper if you're particularly interested in this. But one way you can think of domain is mathematically, it's a joint distribution over the inputs and outputs, and it differs over domains 1 and 2. So it looks like this. So a lot of people, when they say domain, it's like they think specifically of like topic, or they think specifically of something else. But you can also think of it as like the mathematical definition of the domain of the function, the data that goes into the function. And from that point of view, this, any shift in distribution would qualify for this. In practice, it can be content, style, or labeling standards. So content is what is being discussed, style, the way it's being discussed, or labeling standards if we're asking people to annotate data the way the same data would be labeled. Another good thing to think about is the type of domain shift that you're dealing with. So there's two kind of technical terms that we talk about when we're talking about a domain shift. And one is covariate shift. And covariate shift is basically the input changes, but not the labeling. So we see that in domain 1, in domain 2, they have a different distribution over the input, but the distribution of the output given the input is the same. The second one is called concept shift. And in this case, the conditional distribution of the labels changes. And this can correspond to different labeling standards. So basically, the conditional distribution here changes. So which one of these two seems like a harder problem to solve? Yeah, the second one. So the second one is much harder because like there's no way to come up with a good model that does well on both without knowing which domain it's in. Just to give a very obvious example, let's say you're translating into different languages. Let's say you're translating into Hindi and Chinese. That would be an example of concept shift. And there's no way you can come up with a model that does a good job if you don't know whether you're supposed to be translating into Hindi or Chinese, right? Pretty obvious. However, if you're translating from Hindi or Chinese into English, that would be an example of covariate shift, because the translation into English is fixed, but you might be shifting across. So that's still a hard problem, obviously, but at least you can come up with a model that does both well. Okay. So now I'd like to talk about domain adaptation. So domain adaptation, basically what we do is we train on many domains, or we train on a single high resource domain and then try to adapt to other domains. So this is one example here. And then we are usually testing on a low resource domain. We're testing on a domain where we don't have enough resources to train a model well solely on that domain. And there's supervised or unsupervised adaptation. Supervised obviously being where we have labels in the domain, unsupervised where we don't. Another thing that we need to worry about is domain robustness. And domain robustness is basically training on many domains and trying to do well on all of them. And actually, in practical settings, this is often more important or equally important as doing domain adaptation, because, like, for example, let's say you're a big company and you have lots of users or clients or something like that. You very often will not know, like, just to give an example, let's say you're running a web translation service, you might not know where the text came from. And so you want to be robust and be able to translate text in different domains as well. In order to do this, you need robustness to minority domains, zero-shot robustness to domains that are not in the training data. Okay. Any questions about that? Yes. So transfer learning is where you train on one domain. In this particular context, you would train on one domain and try to create a model that is good on another domain. So basically, domain adaptation is transfer. It's a variety of transfer learning. Zero-shot learning and one-shot learning, like one-shot learning, you have one training example, zero-shot learning, you have zero training examples. So in this case, you could do zero-shot adaptation, where, for example, you have no training data from the domain you're interested in, but you still want to do well on data in that domain. What would zero-shot learning, here's a quiz. What would zero-shot learning without transfer learning look like? What would be a good name for that? Yeah, unsupervised learning. So basically, there's zero-shot learning with transfer learning, where you're transferring from, you have labeled data in another domain. You have labeled data in another domain, but you want to transfer to a new domain. And then zero-shot learning with no data whatsoever would be unsupervised learning. And you'd be trying to, like, discover clusters or salient structure or something. Okay, moving on to multilingual learning. So there's many languages in the world. This is a map of only the endangered languages in the world, with red and orange indicating the level of endangerment. And so you can see there's many languages that we'd want to be working on. Yes, yeah. So zero-shot learning without labels. So the example of, like, k-nearest neighbors clustering would be an example of that. So basically, you're trying to learn something. Zero-shot learning means learning with no training data for the task you're interested in. And so if you're trying to learn without any data whatsoever, that's unsupervised learning. An example of that would be like clustering or something. So yeah, that's another one. I had two questions on Zoom. I just found an example. So do multilingual models also count under domain adaptive models? Yes, in the broad sense. So in the broad sense, they have a different data distribution. So I would call that a domain adaptation, especially if you're starting with a model in one language and adapting to a new one. Many people wouldn't necessarily call it domain adaptation. Usually you'd call it like cross-lingual transfer or something else. Cool. Okay, and so there's many, many languages in the world. And another thing is, like, when I say languages, actually there's many different varieties of things that are traditionally considered the same language. So like American English, British English, Indian English, Singaporean English are all obviously different. And there's also finer grained distinctions between like my English and somebody in the south of the US. If you haven't seen the, especially if you're from the US, if you haven't seen the New York Times dialect quiz, it's very impressive. You fill in like 20 questions and it tells you exactly where in the US you're from. And it gets me exactly right every time I take it, which is once every 2 years or so. Yeah, so anyway, many different ways that people speak, and there's similarity across languages. So yeah.
For folks who are in the LPI, on the 6th floor, I have a poster on my wall of the dialect map of North America.
Okay.
And there's a red circle around Pittsburgh is the main reason I think.
Okay. So so if you didn't hear, Bob has a dialect map of North America, and you can go see it next to his, yeah. So maybe the most interesting one, just to show people, is I'm not, maybe people will know this already, but like how you say fuzzy carbonated drinks is the most famous distinction. And so this is the distribution. And basically blue is where people say pop, red is where people say soda, and green is where people call all of these Coke.
And they really do that.
And they really do. Like I'm not joking. So Pittsburgh's kind of on the border. I'm from Michigan, so we're from pop country, but I can also yeah, and Bob's from Ohio, so and so I'm from pop country, so I called it pop while I was growing up, but now I've like homogenized and can say soda or pop interchangeably depending on who I'm talking to.
I usually say soda pop.
Soda pop, yeah. So that's the safe, easy way out. Okay, but anyway, so similarity across languages. Languages are similar, share similar word roots. So this is an example. There's kind of two reasons why words are shared across languages. One is due to cognates, and cognates are words that came from the same lineage. So like as languages evolved, they came from the same original word. Another example is loan words, which are borrowed from another. So a very important word, coffee, is, I believe, originally Arabic, and you know, was adopted by a lot of other languages with the spread of coffee throughout the world. So another thing is languages share many languages share a considerable amount of underlying structure, like word order and grammar. So even if the languages are very different, like English and Chinese, you can see that basically the structure is pretty similar with some differences. Like there's no to in Chinese here, and there's none. This is a counter that you put after numbers in Chinese, but which doesn't exist in English. But other than that, these sentences are nearly the same in structure. And it's similar between, like, for example, Japanese and Turkish, or Japanese and Korean. So you know, lots of shared stuff. Okay, so because of this, we can do multilingual training. I teach a whole class on multilingual NLP, so there's a lot to say about it. This time we have 1/3 of one class, so I'm going to cover it briefly. But basically, it has to do with you know, taking in multiple languages and running it through an NLP model. This is definitely our best tool right now for applying NLP methods to low resource languages. And we can also think of languages as domains as well. So multilingual learning is an extreme variety where a different language is a different domain. And we can do adaptation to improve accuracy on lower resource languages by transferring from higher resource languages. And we can also do robustness. So use one model for all languages instead of one for each, but try to create a model that's good at all of them. At the same time, there's more complexity. It requires modeling similarities and differences in lexicon, morphology, syntax, semantics, culture across all the languages. So, as I said, far too much to say about it for this one class, but you can also view it as a domain adaptation problem. Yes.
I'll just try to form the question as I go on. So, has something like an auto-encoder method been tried that, say we cross in 5 different languages into the model, and we try to have it reconstruct its translations each time it passes through, instead of having, say, Uno turn to Uno, but we have Uno turn to one, and every other language. So essentially, the idea being that the internal, or the bottleneck representation is common for all the words in different languages. So then from there, that latent space would allow us to be measuring that.
Yeah, so very good question. Is there something like an autoencoder where you basically encode into a single vector and then like translate? And there's actually a very popular method called laser that does basically that. So yeah, it's a good idea, but you know, it's a good idea called laser. So next, parameter sharing methods. So now we're getting into some details of how we can like do multitask learning more effectively. So the very most obvious way to do multitask learning is basically share all of the parameters. So we have a single model for all of the domains we want to be working on. This is simple, and it's actually pretty widely used and reasonably effective. Another thing you can do is share some model components, but not others. One example of this would be like if you share an encoder, but have a separate decoder. This is better because it gives you more parameters, which allows you to be more flexible in some ways. But it also, you know, it causes you to have more parameters, and those parameters might not be learned well on the very low resource languages. Sorry, domains or languages. Another thing that's very popular nowadays is a very small number of unshared parameters. So you share the great majority of the parameters in the model, but you have a very small number of unshared parameters. So this could be like a single embedding specifying the domain. So full parameter, oh yeah.
Just even like them choosing certain like things like Polish and somewhere. The weird thing about it is that most of the cases, and like also it's sort of a dialect, and it's similar to Serbian and Russian, but not the same. So I'm just imagining that versus like another language that maybe is different in
Yeah, so this is a really good question. To repeat the question, it's basically like, which method we use depend on the specifics of the domain adaptation or the language adaptation situation that we're handling? And yes, definitely. If it depends on how much data you have to train the models, it depends on how complex your task is. So for some tasks, you need to share fewer parameters. For some tasks, you need to share more parameters. For machine translation, you would need to share more. You would need to have more unshared parameters to deal with the complexities of the different languages. But if you were just doing tagging or something like that, you might not need as many. So definitely. Yeah.
Here, does it mean that the single embedding is being added to different domains?
Yeah, let me go through the slides that I'm about to show, and then we can get back to that if you have any questions. So I have another question on Zoom. I see the question, but let me get through this first, and then I can go back to that too. Okay, so full parameter sharing, basically what we do is we ignore the domain differences, as I said before. This is a standard first step. You should definitely start out with this before you start doing something more complicated. This is also done multilingually. So for example, you can do multilingual machine translation into English or multilingual pre-trained language models. One of kind of the big shocks of like, I don't know, 2019 or so was that people took the BERT model and then they just trained it on many different languages, and it turned out that that was like good enough to do a really good job of recognizing, you know, for example, parts of speech in other languages where the model hadn't even been trained before. So this is something you can do. Our work on multilingual machine translation into English, this was kind of surprising to me because we trained a single multilingual machine translation model into English, and it still could translate other languages that it had never seen before, just because they were similar enough to the languages it had seen in training. So this is a very powerful technique that you should definitely consider if you're doing multilingual training. However, one thing about just full parameter sharing, where you share all of the parameters of the model, is that it can never achieve ideal accuracy under concept shift. And as you remember, concept shift is when your conditional distribution changes. So if you have a single model, it can only express one distribution, right? So you need to, you will not be able to express like multiple distributions. So a very, very simple way to break this, or to fix this problem, is having a domain tag. And what I mean by a domain tag is basically this. Before you take in any text, you append a tag that basically says, this text is from the news domain, this text is from the medical domain, or this text is from English, this text is or this text is being translated into French, or this text is being translated into Japanese. So this is not full parameter sharing of the model, at least when it's implemented in this way. It has a very small number of unshared parameters. And how many unshared parameters are there between the different domains? Any ideas? Yeah. One embedding for each tag, one embedding for each domain. So like, let's say your input embedding size is 512 and you have 10 domains, that would be 5,120 extra parameters. Compared to the 15 million parameters in your model, or 175 billion parameters in your GPT-3 model or Bloom model or something like that. This is a very small number. Also, if you want to get around like adding any parameters at all, you could just put like French, Japanese, like the actual words there, and then you could just reuse the existing embeddings as well. And you wouldn't be adding any extra parameters, but you'd still be specifying that there's some domain shift. Yeah. Yeah, probably would be. So then you might be in trouble. So the question was, what if the word French, what if your sentence started with the word French? Then you might have the problem that I showed at the very beginning of the class, where it was like, who invented neural machine translation? And would give you who invented neural machine translation. Okay, cool. So yeah, so this introduces a very small number of parameters. One issue with this is minimal parameter decoupling is often insufficient or inefficient. So one reason for this is, for example, in multilingual learning is kind of the extreme domain adaptation setting. In a fixed size model, the per language capacity decreases as we increase the number of languages. And so then increasing the number of languages decreases the quality of all languages accuracy. So this figure over here is a nice figure where they demonstrate what they call the curse of multilinguality. They are showing the scores for all languages, or actually I'll use my mouse so that people on Zoom can see. They are showing the scores for all languages, high resource languages and low resource languages. And basically what you can see is high resource languages here are the best when they only add a small number of languages to the model, and then they gradually decrease as you add more languages to the model. Low resource languages bump up a little bit as you add more languages, but then they drop off as well. And you can see overall, keeping the model size the same as they increase the number of languages, like they're not able to maintain the accuracy of even a model that's like reasonably large here. I forget the actual size, but it's on the order of like high 100 millions or billion parameters. So. So the orange accuracy is on high resource, the blue accuracy is on low resource, and the gray is the average between all of them.
Both for train and test.
For test, yeah, test and then.
How similar are the languages?
So I believe these are quite different. They're so in terms of how similar the languages are, I think this is the highest resource 100 languages in the Common Crawl data set. So it's just the highest resource 100 languages on the internet, and those can be relatively diverse. You know, like Chinese and Japanese are certainly in there along with English.
There's like also there's the number. Maybe 5 of them are.
Yeah, and how much does it's basically like maybe the scores are decreasing because the languages are very dissimilar, and yeah, that's certainly the case. The more similar languages are, the more, you know, the less you'd see this drop off. Like similarly, the more similar domains are, you know, it's not just about languages. We see a similar thing in domains as well. Because of this, you can do more aggressive parameter decoupling. So one example is in like multilingual learning. You could have one encoder or decoder per language. So that completely, like in a sequence model, this completely decouples. This, you know, in our age of very large models is not practical anymore. So that's like too much decoupling, basically. And so now there's a lot of kind of work on nice parameter efficient methods that maintain high accuracy, but nonetheless allow us to learn over many different like domains or tasks or other things like that. The most famous example is something called an adapter. And what the adapters do is they add a small layer per domain or per task to an already trained model. And this is an example from the transformer architecture. And the way it works is this is, you know, the standard transformer that you saw 2 classes ago and are certainly implementing now. And you take the adapter and you stick it in here. Within the transformer layer, and the reason why this is a good idea is because this means that you can share all of the parameters in the gray and green sections here, so like most of the transformer parameters are the same, but just this adapter layer is learned. And another kind of key point of these adapters is that very often they use a down projection, a nonlinearity, and then an up projection. And so what that means is the more aggressively you down project, the smaller number of parameters you're using. So you could be down projecting to like even just a single hidden node, and then the number of parameters would basically be like, or the total number of parameters added by each adapter is your normal hidden state. And let's call it the bottleneck. So the bottleneck is the like small hidden state represented by 2 here. And so it's B times H times 2 because you have your down projection matrix and your up projection matrix. So this is much smaller than, you know, what you're using in the transformer or whatever else otherwise. Are there any questions about this? Yeah.
And this is for each transformer layer or just
usually you put them in every layer, but that's also completely optional. You could design it however you want. And actually I should have put this on the slides. I just realized I missed it, but we have a paper that we published this year on that's called Toward a Unified View of Parameter Efficient Transfer Learning. So if you're particularly interested in this, number one, I like this paper a lot, so I'm very happy to talk about it if you want to talk to me about it. But it also kind of organizes a bunch of different methods for parameter efficient transfer learning, including adapters, prefix tuning, LoRa, other things like this. And we kind of like compare and contrast them, how they relate to each other and other things. So if you're interested, I'd be happy to talk about that with you. Cool. So are there any questions about this? Yeah.
I'm curious. So in our adaptive, our main goal is not to reduce parameters. So something like in convolution nets, they tend to have blocks which first blow up in the middle, so they can do high dimensional calculation and then bottleneck the background. So and this, I'm guessing, would instead reduce the amount of dimensionality which you can do some computations. So is there like a trade-off that was considered?
Yeah. So the question was, normally when we are doing things like convolutions or other things like that, we expand the dimensionality so we can learn lots of features. And in fact, that's exactly what the feed-forward layers do in transformers, right? The feed-forward layers in transformers normally blow up your dimensionality a lot so you can extract features and then bring it back down. You already have those layers in the shared transformers, so the idea is that the adapter can be very slim but still give you adaptation. The second question was, is there a trade-off? And the answer is definitely yes. So if I go back to the paper I just showed, I believe we even have a yeah. So basically, this is a graph that shows the trade-off for various methods that you could be using. And basically, the way you control this trade-off is by how big the bottleneck dimension is for these models. It isn't. I forgot to put it in. I could add it. I added it to Zoom, but also I can show it on the screen. So toward a unified view of parameter efficient transfer learning. Cool. If you miss it, I can put it on Piazza later. So one question is, so the question, to repeat it, is basically like, one thing that could affect your results is if the data is available all at once, or if it's available sequentially. How does that interact with parameter efficient tuning methods like adapters? That's a good question. I don't actually know the answer to that, or I don't know of any papers that have looked at that. I'm not saying they don't exist, but I just like haven't seen one. So, I mean, I can guess. What I do know is if you only want to adapt to a single task, it's very often fine to just fine-tune the parameters of the entire model right at the end. If you want to maintain accuracy over tasks, that can be hard without adding additional parameters. There's a whole like field of continual learning where they try to like do this effectively. When you add parameters, the best methods for continual learning add parameters. So maybe it's an indication that like even in sequential learning, adapters are very helpful. But yeah, I don't know about something that's asked the question in like exactly the way that you mentioned before. Okay. So another thing is regular. Yeah. Sorry. Are we doing an adapter for every domain that is coming in? Very, very good question. The answer is it's complicated. So normally you do that, but there's some work, multiple types of work that try to combine adapters in different ways. This is one of them. It's called adapter fusion, and basically they try to combine together multiple adapters in interesting ways. Like, for example, you can have one for a task and one for a domain. You can have multiple adapters and do like linear mixtures of them and other things like that. So if you want to make it more complicated, you can, but normally we just learn one for each domain. Cool. Okay, so yeah, I will move on. So regularization methods for adaptation. So pre-training and fine-tuning, as we know, is a very widely used method in NLP to do adaptation to particular tasks. Pre-training actually relies on the fact that we won't move too far from the initialized values. So if we could move arbitrarily far from the initialized values that we're learning using pre-training, basically pre-training and regular fine-tuning would be essentially the same, right? You know, they would both fit the training data perfectly and not do so well on the test data because they'd overfit. So we need some form of regularization to ensure that this doesn't happen. And the easiest way to do this is early stopping. So early stopping is a form of regularization. And specifically, it's a form of regularization that encourages us to stay close to our pre-trained parameters. There's more extensive like proofs of this, and they actually, link together early stopping with like L2 regularization or things we know about normally. But to give a very simple example, let's say this is our pre-trained model parameters. This point here is our pre-trained model parameters. What if we did the like infinitely strong version of early stopping of not training our model at all? It's regularized to stay the same as the parameters, right? Let's say we only took one step away. Basically, we're limited to be only as far away as like a single step according to our current learning rate would be. So like as we train, we might get farther and farther away, and the longer we train, the farther away we might be getting. So basically you can think of like training longer. Training shorter is a form of regularization that keeps us close to our regular initialization. So that's why I call it implicit regularization. We don't have anything in our loss function, but it still keeps us close. There's other things like explicit regularization, L2, on the difference from the initial parameters. So here we have our adapted parameters, which are equal to our pre-trained parameters and the difference between them. And then we have like the L2 norm of the difference between the two. The L2 norm, is more explicit, but in reality, I've never gotten this to work like really, really well in adaptation scenarios, and the early stopping seems to be, sufficient, or at least it's hard to do better than early stopping with respect to that. Another version of regularization is when you're doing adaptation, you just increase the rate of dropout in your model, which is actually, I don't know if I've covered dropout in this class yet, but basically it's where you drop out, where you zero out some of the inputs. Maybe I covered it. But anyway, so like these are some versions. I personally wouldn't recommend bothering with explicit regularization, but maybe other people have had different experiences. Okay, so another thing is soft parameter tying for multitask learning. It's also possible to share parameters loosely between various tasks. And you can do things like regularize parameters to be closer, but not tied in a hard fashion. This is just one example. It's kind of an older example where they had different layers. And what they did is they basically had a model that was trying to do parsing. And it had embeddings for each of the words in different languages. It had embeddings for part of speech tags in different languages and arcs in different languages. And because the words in different languages are different, they did no regularization whatsoever. But because the parts of speech and arcs are, there's syntactic information that's actually shared across the language because they use a shared annotation standard. So they did regularization between these embeddings. However, a noun, due to differing annotation standards, a noun in one language might not exactly overlap with a noun in another language, or probably like function words are even more diverse. So basically they allowed the mapping to be soft instead of hard and demonstrated that this improved accuracy. Okay. So finally, I'd like to talk about another parameter sharing method, which is selective parameter adaptation. And sometimes it's best to adapt a subset of the parameters of your model. So for example, in cross-lingual transfer for neural MT, this is a famous paper where they basically demonstrated that when you're adapting to new languages, sometimes it's better to not adapt all the parameters because it causes you to overfit on a small amount of data. So they basically, I believe they were doing like French English translation to Uzbek English translation or something like that, where they adapted the source and target kind of sequence encoders, but then they didn't adapt any of the embeddings, and that gave them better accuracy. Or didn't adapt any of the target embeddings, and that gave them better accuracy. There's also versions of this for the transformer. So it's basically, you can decide which subnetworks of the transformer to be sharing, like the feed-forward networks, the self-attention networks, and other things like this. And this is a paper I did with a master's student here. And basically what we found is it depends on how diverse the languages you're using. So that goes back to the question we had before about like the importance of diversity or similarity between the languages. If you have more diverse languages, adapting more parameters is better, unsurprisingly, but it's a good data point to know. Cool. And then the final thing, this is a very nice technique that you can be using, which is to try to regularize the feature space between different like domains or languages, for example. And the way you can do this is like, let's say we're doing text classification in many different domains. We have our feature extractor, which could be, a transformer or anything else. And then we have a label predictor that tries to predict a class label for each. Let's say it's a sentiment analysis. What we do is we add an additional task of trying to predict which domain this data came from. And what we do is we try to train this feature extractor so the domain classifier does a really poor job at classifying the domain. And the way we do this is we train the domain classifier with normal gradients, but then we flip the gradients to try to make sure that the feature extractor is trying to increase the loss of this domain classifier. And we're going to cover this more in later classes, but that's the basic idea. And the reason why we might do this is if you look at the feature spaces of different domains, if you just train like a feature extractor organically, you'll see that the features will have something like this is domain 1 and this is domain 2. And then this would be like positive sentiment in domain 1. This would be positive sentiment in domain 2. And so because the domains are disjoint in the feature extracting, the positive labels are also disjoint across the domain. So what this feature space regularization does is it basically ensures that the features in the two domains lie in the same space. And that increases the possibility or the probability that positive labels will be in the same space when we do this. So this is easy and very effective at doing domain adaptation. So I'd suggest it's something to do.
Is this like again, but both models are distributed?
Yeah. So this is like again. So I like to call this adversarial feature learning because it's not generative adversarial networks. It's not generating anything. But basically it's you have you have a classifier competing with the feature extractor to try to move the features in opposite directions. So it is like an adversarial method.
Is it possible to, I mean, in this specific case, is it possible to study the correlation between the features and then do a sort of a non-linear feature transformation?
Yeah. So the question was, is it possible to study the correlation between the features and do a non neural feature transformation? There's a paper by Michael Jordan and others, Michael Jordan from Berkeley and others, and basically they're doing something like this. That actually happened right before this paper that I'm posting here. It happened in like 2015 or something like that, and I think this method won out. More people are using it now, and the reason why is just this is so easy to implement compared to like doing some other post hoc processing. So there might be, that will give you a better global view of the whole you know, like the whole space. So it might actually be better, but this is, you know, you add one extra layer to your neural network. So I think a lot of people use this. So I had a question. What is the difference between feature space regularization and something like Z normalization of features? So I think the important thing here is this is ensuring that the two feature spaces are the same, whereas Z normalization of features wouldn't necessarily do that in a systematic way. It could like maybe move these things together, but they would be swept over or something like that. So Z normalization, you have to do post hoc also. So yeah, it's a good question. I'd have to think about it a little bit more to give it like a mathematical definition, but I think you learn this jointly with the models, so that makes it a lot easier.
Sorry, there's also kind of instead of the very so when coming with a batch norm also kind of different.
So this looks like covariate shift. Would something like batch norm fix this? So if it did, I think it would be because you're lucky more than because it was specifically designed to do something like that. Like batch norm, just so people know, batch norm, it tries to normalize so that every batch has similar like statistics, like mean and variance across all of them. I can't think of any reason why that would necessarily make the domains distributions match. So, okay, moving on. So another thing I'd like to talk about, this is the second like major method that we have for multitask learning is task weighting. And when we're handling different tasks in learning, we want to decide how much to learn on each task. So task weighting, basically what it does is it differently weights loss functions from different tasks. So we basically multiply the loss function by a scalar. Task sampling is similar to weighting. But what you do is you modify the sampling proportion of examples from each task. So for example, if you have a sampling ratio of 0.8 to 0.2 for task 1 and task 2, you would just sample more examples from task 1. Then the other question is when to learn on each task. And this is often referred to as curriculum learning, choosing the order of tasks appropriately so you do well at the end of the training. Pre-training and fine-tuning is one variety of curriculum learning. It's a very specific variety of curriculum where you start out with one task and then follow with the other one. There's, of course, other methods for curriculum learning that you could use as well. So some simple task weighting or sampling strategies. Uniform is the most simple one, obviously. You weight or sample the tasks with equal probability. Another one is proportional sampling or weighting. And when you do this, basically what you do is you sample or weight tasks according to the data size. So this is exactly what would happen if you just like combined all your data together and then did training over all of your data. An obvious issue with this is like, let's say you're training on English and Telugu, like I talked about before, you're going to have 2-3 orders of magnitude more data for English than you do for Telugu. So basically the higher resourced language, or we could also be talking about Wikipedia or medical text, and or like regular net text and medical text, and you'd have much more net text. So basically, the overrepresented domain will do much better than the underrepresented domain. One very simple way to fix this, which is kind of the standard in multilingual learning now, is a temperature-based weighting of the tasks based on their size. And so if the temperature is equal to 1, basically we follow the data distribution exactly. If the temperature is equal to infinity, we have uniform weighting. So temperature equal to 1 is equal to proportional. Temperature equal to infinity is equal to uniform. And anything in between is like a mixture of the two. It still upsamples some more frequent tasks, but it doesn't do so as drastically as if you use proportional weighting. And so this is pretty commonly used in a number of contexts. You can also, yeah, go ahead.
What's the advantage of loss weighting versus sample weighting?
Yeah, very good question. So what's the advantage of loss weighting versus sampling? So basically, in the limit, sampling is a way to approximate loss weighting. So let's say you had a loss weight of 0.8 and 0.2, and you were doing full batch training, not sampling. If you were doing full batch training, and you weighted one task 0.8, the other one 0.2, basically you could reapproximate that by sampling an infinite number of times data from each of the tasks, and that would give you the same result. So basically, they're in the limit, they're equivalent. So then the question is, not in the limit, practically what's different from them. One advantage of sampling that makes it very attractive is that, let's say you're doing two very different tasks, like language modeling and parsing. If you sample one batch, you only need to encode one batch at one time. So you can use your language modeling code for one batch, your parsing code for another batch. So that makes things easier, I guess. The other thing, the kind of disadvantage of sampling is that you might take one big step in the language modeling direction, then take another big step in the parsing direction, take 3 steps in the language modeling direction, 2 steps in the parsing direction, and it could kind of make training less stable because there's less of a uniform distribution over the inputs. Yeah. Very good question. So the question was, is data set size correlated with the kind of difficulty level or the difficulty of learnability? So I'm going to go to that right now. So one really important thing is when you're considering 2 tasks, if you think about how we learn machine learning models, we learn them with gradient-based optimization. And so one issue is what if you have one task where the loss value or the scale of the loss values is just way bigger than the other? And let's say we were doing them in the same mini batch. Basically, the task with larger loss values would just completely wash out the other task because you're getting gradients that are 100 times larger or 1,000 times larger. Practically in NLP, can anybody think of an example like this? What would be a task with a very large loss per sentence, for example? Or alternatively, which one would probably have one of the lower loss values? Or actually, maybe another way to think about it is, let's say you had a uniform distribution over all of your choices. What kind of task would have a very large loss value? or a very small loss value. So like right at the beginning of training when you know nothing about the task whatsoever. Okay, I heard sentiment classification, and that would be lower. Yeah.
And maybe something like ASR would have very high.
Something like ASR would have very high loss. ASR is a good example. Anything where you're generating text is a good example. And the reason why is because text classification, let's say we're talking about binary text classification, the highest log likelihood you would expect to have is like, or the highest loss you would expect to have is 0.5 per sentence, because you have two choices. So you just do 50-50 and that would be your loss. But for language modeling, it's like the vocabulary size for the number of words in the sentence. So this is literally, probably orders of magnitude larger, right? So that's a problem if you're like learning jointly with both of those tasks. So a very simple solution to this is basically normalizing by this kind of standard deviation term here. And what this method does, this method by Kendall et al. Does, is it normalizes by the standard deviation term, but it allows you to learn the term. And it also adds a regularizer to prevent the term from getting too large, because if the term became infinity, your loss would go to 0, and then that wouldn't be very interesting, right? So this allows you to scale losses from different tasks. So actually, sorry, I should just call it sigma. It's not actually the standard deviation. I called it standard deviation because it's a sigma, but basically it's a learnable parameter that allows you to like weight the losses. Another thing, we actually talked about this last time, but it's Lucio's work where you specifically optimize the loss, and you optimize the loss based on the similarity of the gradients between the task that you want to be solving, the black task here, so this is the target one, and the other like auxiliary tasks that you're using. So you have the blue gradient is close to the black one, so you upweight that because it's helping you move in the same direction as the final task that you want to be solving. Okay. Okay. So another thing is choosing the tasks that you could be using to transfer from. There's different ways to do this. One way to do this, which is the one that I use most of the time, is intuitive selection. So more similar tasks you would expect to benefit more. Yeah. So like, for example, if we're talking about multilingual learning, training on more similar languages, you would expect to do better. And if you're talking about like domain transfer, more similar domains also. Another thing is you can do empirical selection. So you can run many transfer experiments and deduce rules. So in this paper here, this is one of our papers. What we did was we trained a very, very large matrix of transfer experiments where we trained on one language and then transferred to another language. And that allowed us to find the actual kind of like gold standard best languages to be transferring from. And then we trained a model to try to predict these. So the way, basically, what the model told us was like what features of the language or the language pair are most useful for deciding whether these are close to each other. And some examples were, are the two languages close in geographic distance? Are they spoken at similar places on Earth? Or do they share a lot of vocabulary overlap, other things like this? Yeah.
So, like, if you have two languages which contribute to one language, and if you use both of them in transfer, does it lead to more than
Yeah, so good question. So if we have two languages that contribute to one language, so like, for example, if we have one language that's similar in syntax, another one that has lots of loan words or something, would that help? Yes, it probably would. I can show you the spreadsheet for this paper. We actually have the spreadsheet for this paper at the bottom of our repo. But The spreadsheet for this paper, you'll see why we didn't do that experiment. Because it's at the very bottom, the raw data. And in order to do that, we would need to not run experiments between two languages, the training language and the test language. We'd have to run it between three languages. And so if you look at our machine translation results, this is how many machine translation experiments we ran to do that, to create this paper. And if we start going from a matrix to a tensor, probably I would be contributing more to global warming than I would prefer to be doing. So I decided to not do that. A final topic that I'd like to talk about before we run out of time is a very nice topic that's been examined. Oh yeah, sorry, go ahead.
We have worked with trying to understand student learning in India and various from Hindi and Tamil. So we actually found that I think we have to training on both Hindi and Tamil.
Yeah. So just to repeat the comments, so it is the case where they saw before that training on Hindi and Tamil helps Marathi more than training on just one, because it kind of borrows from both of them. So I totally think it is the case. What I wanted to say is we didn't investigate that systematically like we did in the previous paper, because that would have been a lot of experiments. So distributionally robust optimization is an interesting idea that we'd like to find a model that does well over multiple domains. And the objective is this: the distributionally robust optimization objective optimizes the worst case loss. So it basically optimizes the loss on the task where we're doing worst. So to give an example of multilingual learning, this would be like optimizing the loss on the language where we currently have the highest loss. And the reason why this is good is because basically it ensures that no task is left behind in our optimization. So it tries to do well on the worst task. One problem with this is if you have something that's just really, really hard, a task or a language that's really, really hard, this can overfit to like a very low resource language and cause issues. So there's some tricks that you can use to fix them, like the tricks in these two papers that I cited today. Okay. And I'm going to run out of time to talk about inherently multilingual considerations. You can take a look at them on the slides. But yeah, thank you, everyone. Is there any last question before we wrap up? Or... Okay, thanks a lot. I see one question. What would the loss look like over multiple training examples or batches? So basically, when we're training over multiple training examples or batches, we usually track the max over multiple examples. So we take a rolling average or something like that. Or in the case of this paper by Zhou et al, down here, we actually do a whole epoch basically before we measure which one the max is. So yeah, you need to aggregate over multiple ones.